Okay, this is Mr. Huizenga here. I'm going to go over section 5.1 with you. This is an opportunity for you to hear the lecture again in case you need to review it, or if you did miss the lesson, this would be the opportunity to hear it from the classroom perspective. The main ideas here from section 5.1, you have 7 different learning targets. I'm going to ask you to relook at these things at the end of the lesson to make sure that you understand the material pretty well. Let's go ahead and progress into this lesson. So you guys did a little bit of reading already on this idea of work. And so the question is whether or not the woman is doing work as she pulls that crate along. Now certainly it looks like she's straining, she's spending some energy to be able to pull that thing along. That's sort of the way that we would use the term work in an everyday sense. The term physics work means something a little bit different, and so the question is she doing work? And the answer is yes, she is. Work is done on an object whenever a force acts in the direction of the object's motion. In this case here, she is exerting a force in the direction that the object is moving, so she is, by definition of the term work, she's doing work on that crate. Now, we need more than just to say she's doing work. We want to be able to quantify it. So how we quantify work, we'll start with the equation down here. As an equation, the amount of work that a force does is essentially equal to the amount of force exerted multiplied by the distance that object moves while that force is exerted, multiplied by the cosine of the angle between the force and that distance that it moves, or the displacement. It's pretty complicated here, so we want to look at the word equation to figure that out. Work done by a constant force is computed by multiplying the distance the object moves, that's d, by the component of the force that acts in the direction of the object's motion. Now you can see that's where that cosine of theta comes in. If you think about vectors, and force is a vector quantity, if I take a look at that force acting along that direction, there's really only a component of that force that actually does work. The component that's in the direction of the object's motion, that would be called F parallel, or the component of the force that's in the direction of the displacement. That's actually F times the cosine of theta. The other component of that force, which is this vertical component, actually does no work. That perpendicular component does not contribute to work being done on that object. So that cosine of theta is there simply to take the component of that force that acts in the direction of the motion. And we'll be looking at that concept much more as we progress through today's lesson. Okay, as usual, the details become pretty important when we're considering work. There must be both a force and a displacement for there to be work done on an object. So is there work being done in these 3 situations? This is just a picture of a person, strongman competition, pulling a tractor trailer. There's a rope attached to his waist, and back here is a tractor trailer. And the objective here is for him to pull that trailer a certain distance, and whoever pulls that trailer the fastest, or with the least amount of time, is the winner. So is he doing work? And the answer is, of course, yes. He is exerting a force. There's a force from the rope that's acting in the direction of motion, so he's doing work. Now these other 2 situations are a little bit more complicated. This guy's pushing really hard up against the wall. Maybe he's frustrated by his physics homework. Who knows what? But is he doing work on that wall? Truth is that even though he's exerting a force, since there is no displacement, there is no work being done because there's no motion. There has to be a force and a displacement. Here, there's no displacement. How about this guy, hoverboard rider? This hoverboard's a little bit more fancier, if you will, than the one that I have in the classroom, but nonetheless, it is able to allow him to move along without any friction. Once he gets going, is there any work being done on that object? Here we have motion, but no force acting. Once the hoverboard is in motion, there's no force that's acting in the direction that it's moving. That's a statement again of Newton's first law. He's just going to continue to do what he's doing, and he doesn't need to have any additional force acting to keep him moving, so there is no work being done. This bottom picture, more complicated still. This is a farmer, maybe, working, carrying some produce around. Is he doing work on that barrel of produce as he carries it around? The answer to this might surprise you a little bit. Even though he is exerting a force, and the force that he exerts is upward, the direction of the object's motion is actually sort of hard to draw here. I'm going to draw it as a horizontal line, moving it horizontally. You can see that even though there is a force and there's a displacement, he actually does not do any work on that crate because of the way we define work. He's exerting a force, there is motion, but there's no component of that force that acts in the direction of the motion, so therefore that force does no work. And again, he's going to tire out, he's going to expend energy, but technically he's not doing work, the way we defined it, on that barrel. Just as this guy's not doing work on the wall, if there's no motion, there's no work. If there's no force, there's no work. We have to have both force and motion, and they have to be in the same direction, or at least have a component in the same direction. Okay, is work a scalar quantity or is it vector? Hopefully you got this from the reading. Work is in fact a scalar quantity. It's something that has magnitude only, no direction. Now, it's very much like temperature. It can be positive or negative, but it has no direction associated with it. It's probably confusing since force is a vector and displacement is a vector, but when we multiply those two things together, what we end up getting is a scalar quantity. Now, it can be positive or negative. Let's look at these situations down here. Here we have a weightlifter lifting some masses or some weights over his head. Is he doing work? Yes. Is he doing positive or negative work? Well, in reality, he's actually doing both kinds of work. When he lifts them up, he's exerting a force in the direction of the object's motion. So therefore, he's doing positive work. So the force is up and the displacement is up. So he's doing positive work. As he lowers the masses, now what he has, he's still exerting an upward force, but now the motion is downward. And when the motion is downward, we see that the force and the displacement are in opposite directions. He's doing negative work. Here we have that situation again of the woman pulling that crate. Sure enough, she's doing positive work since the force that she's exerting is in the direction of the object's motion. She's doing positive work. There is kinetic friction that's acting. That kinetic friction would be acting in the opposite direction of the object's motion. So therefore, kinetic friction is doing negative work. Can gravity do work? Now, gravitational force always acts downward. So let's go ahead and draw a little arrow here representing the gravitational force acting on that object. And certainly as it's rising, its displacement is in the upward direction. So there's the weight force, there's the gravitational force. That's the weight force, that's the velocity vector. Does that force do any work on the projectile? And the answer is yes. It does do work. In this case, it would be negative. Now over here, while the object is falling, let's go ahead and draw again a weight. Let's draw a force vector acting downward. And now we have a velocity vector also in somewhat of the downward direction. We see that now gravity is doing positive work. Over here I have the moon orbiting the Earth. Gravitational force is always pointed towards the center of the object's motion, so towards the center of the circle. And you can see that the force and the displacement or the velocity vectors are always at right angles to each other, and so there's no work being done by the gravitational force on the moon. To summarize all that, we'll go ahead and summarize that with the statement here. It does work, negative work as the projectile rises. It does positive work while it falls. It does no work at the apex, where the weight force is downward and the velocity is towards the right. And neither does the gravitational force do work on the moon as it orbits around the Earth. Okay, some problems dealing with the work equation. The SI unit for force is Newton, for displacement is meter. Work then is the Newton meter, or named after a guy who did a lot of work in this subject area back in the 1800s. A little play on words there. The Newton meter is named after James Prescott Joule. It's called the joule. 1 Newton meter is equivalent to 1 joule. So let's go ahead and compute the amount of work that she does as she pulls that crate along. Let's give it some numbers now. She's exerting a force of 220 newtons at an angle of 75 degrees from the vertical. Now I'm giving you this angle, not the angle between F and D. That becomes important in the equation. She moves the crate 8 meters. So how much work does she do on that crate? Pretty simple, really. We start with that equation, and when we plug those numbers in, we'll see that she does 220 newtons exerted through 8 meters times the cosine of 15. 15 degrees is actually this angle, and that's the angle that we want. Again, based on theta being defined as between F and D. That's to be able to get the component of the force that's in the direction of the object's displacement. we'll get 1700 joules of total work. Let's do a few more problems. These are for you to do. I'm not going to talk you through these things here. Pause the video, go through and try these couple of problems and see if you can determine how much work each of these two do. And when you're ready to check your work, go ahead and restart the video. Okay, and hopefully you have now progressed through and you've got the answer to these problems. This is actually called a Tom sled, and the reason it's called a Tom sled is because Tom actually did more work. 106 times 13 meters times the cosine of 0 degrees is 1380 joules. That's the work that Tom did. Now for Bob, even though he exerted more force through more displacement, because we have that component of force in the direction of the object's displacement, he actually does less work than Tom. The negative 35 is because the force is at a downward angle to the object's motion. So if this is the direction of the force, and this is the direction of the object's motion, you can see that the angle is negative if you want to think of it like that. But it doesn't really matter because the cosine of a negative angle and the cosine of a positive angle is exactly the same value. Now down here, the catcher, he actually does negative 130 joules of work, and hopefully you paid attention to the fact that that has to be put into meters, and there is an angle of 180 degrees between the way the force is exerted and the way that the object is moving. And so these two things are in opposite directions, so we get that negative in there. Last but not least, we need to be able to do a big picture summary of work. When work is in the positive direction, the forces in the direction of the motion tend to increase the speed. When work is in the negative direction, the force that's opposite the direction of the motion tends to decrease speed. Positive work speeds things up, negative work slows things down. When multiple or angled forces act, any change in speed indicates whether or not we have a positive, negative, or zero net work. When we have lots of forces acting, oftentimes it's more useful to look at the net work done by all the forces. And again, just to reiterate that particular idea, the net work done by gravity as it moves, as the moon moves around the Earth, is zero. There's no change in speed at all on that moon as it moves. That's not true for elliptical orbits. In elliptical orbits, we actually do have a component of force, in this case, that's actually opposite the direction of the way the object is moving. If I think of that as a component idea, I have a component that's acting this way and a component that's acting this way. And this force does no work. This force does negative work. And so the gravitational force does negative work as it's moving away from the sun. And if we look at a similar situation down here where the planet is maybe coming back towards the sun during its elliptical orbit, we see that the gravitational force now does have a component that's in the direction of the object's velocity. So this component is what does the work. That component does no work because it's at a right angle to the displacement. Guys, in a nutshell, that was section 5.1. I want you to take a little bit of time and tell me how you feel on these particular learning objectives. Give yourself a self-evaluation. Feel free to start on those problems whenever you feel ready. We'll see you tomorrow.